solutions to that in the keynote, so nice to hear more.
Thank you very much. So I hope you still have some brains left to listen for yet another, but it's the last talk, so the last talk. It's a bit different in flavor to the other contributed talks, in that I'm talking about actually one big mechanization of mathematics. And it's one chunk of mathematics, namely its undecidability proofs. And the work has been going on for quite a while now. Lots of people are involved, most of them in Saarbrücken. So besides me, in Saarbrücken are André, Edith, Dominic, Fabian, Gert and Maximilian. And then Dominique Lachey-Wondling from Loria in Nancy. And Simon did his bachelor's degree with us, now moved on to Cambridge. Dominic did his bachelor's degree with us, moved on to the University of Amsterdam. Many of us are here, so Simon and Dominic are in the room. Fabian is sick somewhere in the hotel, but you might bump into him later. All right, so the talk is roughly going to have this structure. I start by telling you what our approach to synthetic undecidability proofs is. And then I'll give you an overview of what we actually have in the library, or some dedicated points in the library that I think are interesting enough to mention them here. And then, because it's POPL, I talk a little bit about development issues, because the library has grown quite big. Nobody of us has experience in developing a code base of this size. So there are a couple of interesting questions, and it might be interesting for us to talk to you or for you to talk to us about these kinds of things. And lastly, I'll talk a bit about the future, what we're interested in. All right. So lots of you have done formalization in mathematics, I assume, and probably all of you have at some point used the definition of decidability in Coq. And all the time, when you're saying, okay, a predicate is decidable, you're always usually proving this by giving a function, a Boolean function, such that the return value somehow reflects the proposition. That's completely standard. But you can ask the question, why is that actually okay? Because on paper, at least for completeness, people would say there is a program, there is a Turing machine, there is a Lambda calculus term or whatever computing this. In Coq, we always do it like this, and we rightly do it like this. But the answer why this is okay is, well, first, because Coq is a programming language. And so if you define a function, a Boolean function, that's going to be computable in some Turing complete model of computation. You're not talking about it, but it will exist somehow, at least provided that the type X is something like natural numbers or pairs over things that you know how to compute, and like natural numbers or Booleans or lists of stuff like this. So the definition of decidability is standard and used a lot. Undecidability is not so clear. So the first easy idea would be that you define it as the implication, as the negation of decidability. We have seen decidability, so you could define it as not decidability. It's a valid definition, you can write it down. Unfortunately, this doesn't work because you can never actually prove it. Coq is consistent with very strong classical assumptions. In particular, it's consistent with the assumption that every predicate is decidable. So you will never actually establish this proposition. So you can work in a theory even where you assume, say, the halting problem for Turing machines is decidable and explicitly assume this as an axiom. By some meta theory, you know that this is definitely consistent because the set model for Coq validates every decidability assumption. And also you know it's not provable by the same reasoning as before. The only things that you can prove decidable are actually decidable things, and we all know that the halting problem for Turing machines isn't. So because all definable functions are computable, decidability of the halting problem is never actually provable in Coq. And that gives us an idea how you can define undecidability, namely you swap out the unprovable thing, falsity, by the unprovable thing, decidability of the halting problem. And then you end up at the definition that a problem is undecidable if decidability of P implies decidability of halting. Again, valid definition. This time this is actually provable for essentially everything that you want to prove undecidable. And the reason for this is, or one reason for this is that you can see this as a Turing reduction from halting to P, because in Coq you can define Turing reductions from Q to P as exactly any decider of P can be computationally, because we can only write down computational things, turned in a decider of Q. And then you can prove that undecidability transports along Turing reductions in this sense. And you can build big graphs of undecidability by assuming, if you want to, one problem to be by starting at halting and giving more reductions, Turing reductions from there, and then you have a big graph of undecidable things in this sense. The notion we're normally using for reductions are not Turing reductions, but many one reductions. Many one reductions from a problem Q to P are a function that transports instances from Q to instances of P, such that satisfiability or validity is preserved. And every many-one reduction can be turned into a Turing reduction, so you know that you can transport this synthetic notion of undecidability via the synthetic notions of both reductions. All right. I believe this. I think one should believe this. If you do not believe it's correct, we have a backup plan. So if you now ask the question, how do you prove there is no Turing machine computing the problem? Then the first answer is, don't ask this question. The better question to ask is, there is no lambda term computing P, unless you have very, very, very good reasons, and normally they're not very good. You shouldn't think about Turing machines because they're horrible to mechanize, and you should think about lambda calculus terms. And the answer is, if you really want to know there is no lambda calculus term computing your problem P, you can prove that the many-one reductions you gave before are computable in the lambda calculus. And we support this by tools at last year's ITP. And there was a paper together with Fabian Kunze, where we have a framework where we can basically extract coq functions to the lambda calculus automatically. So if you're given a coq function, say, of type nut to list nut, and then we have a metacoq plugin where you can essentially press a button. And what falls out is a lambda term, which has the same computational behavior, and additionally a proof that it really has this behavior. The proof is done mostly in LTAC. The generation of the term is done based on metacoq. Okay, and then you know, we're not doing this for every function explicitly, but essentially you can write every of our reductions in a way such that you can press the button, get the lambda term, then you have full assurance that this works. Especially you can do this under arbitrary classical assumptions. Then you can turn to full classical logic. You don't have to make sure that everything you write is actually computable, because you can use this to actually prove it is computable in the afterwards. All right. And that's what I just said. Okay, so the vision is we want to make undecidability proofs now mechanizable. And by undecidability proofs, I mean interesting ones, not the undecidability of Turing machines, that we know this one by now. And the thing here is, or our idea is, that we need the library now of potential starting points for undecidability reductions. And then if you encounter a new problem that you want to prove undecidable, and you want to mechanize your proof, you look in the library, what's a nice starting point for your reduction? We already have it, ideally, and then you can build, you only have to go from there to where you want to go, and do not have to start at very basic problems like Turing machine halting. And the big graph of reductions that we have by now is roughly this. We have things concerning in this case, we call by value lambda calculus, so the halting problem of this. We can prove that it reduces to Turing machine, so we have a Turing machine simulation of the lambda calculus, and the other way around, we have lambda calculus simulation of Turing machines. We can go to string rewriting, post-correspondence problem, and various forms of the post-correspondence problem, binary stack machines, register machines, or counter machines that can work with numbers. There's the Fructran language that I will tell you a bit more about later. Hilbert's 10th problem, so satisfiability of the Fantine equations, mu-recursive functions, and then satisfiability, validity, provability, and all these notions in first-order logic. Some notions of context-free grammars, which are undecidable, inhabitation in system F, higher-order unification presented by Simon on Monday, I think, at CPP, so third-order, second-order higher unification. And lastly, provability and intuitionistic linear logic. These are the big buzzwords, a couple of more in the make. And then roughly, you can characterize these problems into 3 kinds of problems that are interesting if you want to work with them. And the first kind of problems are seeds. We call a problem a seed if they work very well as a starting point of your reduction. So if you want to give an undecidability proof, you want to pick a seed. Usually they have this property that they're relatively easy to formulate and relatively easy to understand. They don't have much structure that you have to transport to the problem you want to prove decidable. So because they're good starting points, they should ideally have many outgoing arrows. For instance, the post-correspondence problem works very well if you want to go to logics or also other things. The Fantine constraints, although pretty hard to prove undecidable, are a good starting point because they're structurally very simple. And the Fructran language also, although we don't have much work from there at the moment, is a very good starting point. I'll go into more detail in a bit. Target problems. So target problems are problems that are good as endpoints of reductions, and you want them because this means you can close loops, and closing loops mean you prove the interreducibility of problems. And then essentially we've seen that first order logic is a very good target problem. I'll explain later why. And that the lambda calculus works very well to give reductions into these problems. And lastly, we have everything else, and we call them advanced problems for now. They are interesting to showcase the techniques. They are interesting results like linear logic unprovability or system F inhabitation. But they will likely be not of much use for reductions in the future that you might do. Well, we'll see, but probably not. Okay. So I'll start by explaining you the 3 seeds I gave and give you actually a bit insight in the definitions. So the first problem we ever proved undecidable in this notion was at ITP 18. It was Edith Heiter's bachelor's thesis, and then together with Gerd Smolka, we have this paper at ITP where we proved the post-correspondence problem undecidable. Post-correspondence problem is a problem on sets of pairs of strings. So you have a big set of cards that contain a string, say, in the top half and in the lower half. And then the question is, can you pull enough cards from this infinite set of strings, of cards, such that the top half of the string, if you place them next to each other, and the lower half are the same. You can make this formula, so if you have a pair of strings in your set, then then the set deduces this card. And if you can pick another card, you can put the card in behind, and then you want to deduce something that has the same in the top and the bottom. That works very well as a target problem, as a seed for target problems. Then it can express things like string concatenation, because you need them here, and this very simple inductive predicate, but nothing else. So we've used them, for instance, to prove first-order logic. Notions in first-order logic undecidable, because this is pretty easy to characterize in first-order logic. The second seed problem that works very well are the Fantine constraints. That was this year at FSCD with Dominique Lachet. The formulation of the Fantine constraints is pretty easy. So the type you're working on is a list of constraints. And constraints are either saying this natural number plus this natural number is equal to this natural number, or this natural number times this natural number is this natural number, or this natural number is 1. And then such a list of constraints is satisfiable if you have a valuation for them that makes all of them true. Okay? And if you have a problem that can express addition, multiplication, that's essentially enough. Then you can usually prove that your problem is undecidable, because you can encode satisfiability over the Fantine constraints into your problem. Last thing, a bit more esoteric, but helped us a great deal in going to Hilbert's 10th problem, and might be useful for you if you don't have just all the tools you need. So this one has as base type a natural number, which will serve as a state, and the list of fractions, which will serve as a program. And then the idea is that you say that such an instance is satisfiable if the state is terminating under the program. How is the program defined? That's how it's formally defined. I don't think that's very nice to read, so I'll explain it without it. The idea is you have your state, and then you look in your list of fractions, which is the first fraction that you can apply to the state, multiply with the state, such that you keep the state integral. And then you do this all the time. You look for the first fraction, multiply it, it still stays integral. You go on until you don't find a fraction anymore, and then you're stopped. If you want to encode this into your problem, this means that you have to express multiplication and reflexive transitive closure, which is pretty easy oftentimes and can be, so this works very well. For instance, you don't need addition if you don't have this at your hand. All right, now, there we go. Okay, now next thing, target problems. Target problems, as I said before, are the things that you use to close loops. And the one nice target problem appeared, the first nice target problem appeared at CPP last year with Dominic Kirst, who is somewhere in the audience, and Dominique Lachet, no, Gerd Smolka, sorry. And so what you have to do if you want to reduce a problem to first order logic, the idea is that you express the definition of your problem as a first order formula. For many problems, that's pretty easy because you have been using first order tools anyways. And then you prove that the problem is equivalent to the provability of a formula under a context that you can pick before. And the usual proof strategy is from the left to the right. You somehow do induction or use the structure of your problem P. And from the right to the left, we've proved soundness with respect to Tarski models. And then you define your standard model corresponding to your problem P, use soundness, and deduce that if it's provable, actually the problem holds. Next problem is the call by value Lambda calculus. That's actually the oldest work at ITP 2017 with Gerd Smolka. And two definitions. I have to explain one definition and one theorem, and then you see that it's incredibly easy to essentially reduce any problem to the lambda calculus. So the definition is, you can say that the problem P is L enumerable in the call-by-value lambda calculus that we call L for shortness. If there is an L computable function, where you define computability in the way you would define it, an L computable function from natural numbers to the type X, to the option type X, such that P of X hold if and only if X is in the codomain of this function. So standard definition of enumerability somehow, and you need the L computability of this thing. And second, you can then prove that any problem reduces to L halting if it is L enumerable in this sense, and if its base type has an equality decider that you can express in L. And as already hinted at before, that's usually pretty easy. So you can write down the enumeration function purely in coq. You don't have to look at call-by-value lambda calculus. You can give the equality decider purely in coq. That's all very standard. You're doing it all the time already. And then you have to give the encoding for the type X in the lambda calculus. We have tools based on metacoq that essentially make this automatic. And lastly, you have to use the extraction from the ITP paper that I already mentioned that can extract any coq function in particular, or not any, many coq functions in particular, usually functions of this type and this type, to the lambda calculus, and then everything is for free. So you do all the work in coq, press a button, get the lambda term, and then get the theorem that it reduces to L halting for free. All right. Lots of advanced problems that we have. So one of them was at CPP also on Monday by Fabian with Maximilian Wuttke, where we have been mechanizing Turing machines. We've been mechanizing, for instance, the reduction from multi-tape halting to single-tape halting. We've been using these tools by now to also give an interpreter for the lambda calculus on Turing machines, which is a bit tricky. It's not published at the moment. We have higher order unification, as mentioned already, presented by Simon on Monday. So we're reducing PCP to third order unification, and Hilbert's 10th problem to second order unification. And then at Types 2018, André Dudenhefner and Jakob Rehoff from the University of Dortmund have a fully mechanized proof that system F in habitation is undecidable by reduction from Hilbert's 10th problem. And André has joined us in Saarbrücken by now and is working on more undecidability proofs. And CPP last year, together with Dominique Lachet, we proved the undecidability of intuitionistic linear logic, stack machines, and Minsky machines, so register machines. All right. I promised that I'll talk about development issues. So until now, we have about 75,000 lines of code. Because many people contributed, nobody actually understands pieces of code. The development is happening on GitHub by now. It's helping us a lot that we can use Travis CI, so an online program that runs and checks whether this new pull request breaks the code or not. This way, you don't have to compile on your local machine for 45 minutes or something. We're still figuring out lots of best practices. For instance, a big issue is we're still figuring out the best practice to target multiple coq versions. So one solution, the solution coq uses itself, is to have different branches for different versions, which should work, but is a bit of an overhead in maintaining. I'll explain later why. Then it's conceivable that you have one big configure file that you tell the coq version, and then it will set up the repository such that everything compiles. And lastly, we could just scratch all the old coq versions and only target the most up-to-date coq version, which is kind of the most elegant solution from some perspective. The issue now is some parts of the library depend on the equations package. Some parts of the library, in particular the extraction that you need to close circles, depend on metacoq. The newest version of coq metacoq compiles with is 8.9. That's a bit behind the newest versions. That's partially my fault, I'd say. But it's an issue, and it will still be an issue in the future. Other parts of the library have been written in the new SS reflect tactic language, or are using new SS reflect tactics, so they only work under 8.10. So we can't actually target the most up-to-date coq version because we use half of the library. We can also not target old coq versions because then we use, well, not half of the library, but stuff in the library. So actually we have different incarnations of the library living at the moment, and it's not so clear how to do this. Then what about Windows users? They can use equations because it's shipped. They can only, with lots of pain at the moment, use metacoq. I'm not sure whether OPAM is working at the moment under Windows. The last time we tried it, it didn't, at least not for our use case. Then there's the issue, similar a bit, that many people write this code. Different people like different standard libraries. Different people are using different standard libraries, be it the coq standard library, be it standard ++ library, xlib. their personal standard library, and this leads to a lot of incompatibilities if you want to connect the problems, because you have one definition of vector reversal and one definition of vectors, and another definition of vectors that's somehow the same, but not literally the same, and some other definition, and we have to write lots of glue code, which is annoying, or port developments, which is tricky, because, well, if you're not the initial author of the code, it's a lot of work. And then other things that differ between the different developers is we have a little bit of a different trust in axioms. So I haven't mentioned axioms yet, but for instance, I would say it's completely safe to assume proof irrelevance, and you still know that every function of type nut to nut is computable. And there are other axioms, and then you can discuss whether this axiom is actually okay. Can you use this in your computation? Should you be safe? Should you be better not use it? And so that's an issue, and it's an interesting theoretical thing to discuss. All right, and these are the things we want to talk about we want to look at in the future. There are lots of other problems we would like to include. So there's typability in Lambda pi, for instance, or type inference in system F omega that we want to have. There's the intersection problem of two-way automata. They have been mechanized a couple of years ago by Christian Dotschkal and Gerd Smolka. So we could try to plug this somehow. There are one-tiling problems, which are oftentimes used in undecidability proofs for logics. They have a pretty intricate undecidability proof starting from Turing machines. It would be interesting to look whether you can actually find a nicer starting point for this. There are post-tag systems which are still used. There's subtyping in system F sub, typability and type checking in full system F. Many of them might be in reach. Then you can look at entailment in standard kinds of logic, so you can prove that entailment in standard Zermelo-Fraenkel Z-theory is undecidable. There's Trachtenbrot's theorem stating that satisfiability over finite models in first-order logic is undecidable. And one last big, very interesting thing, there's the undecidability proof of semi-unification, which starts at mortality for Turing machines, which is a kind of esoteric, complicated problem on Turing machines, and which would in particular mean we would have to mechanize the undecidability of mortality on Turing machines. And I personally would like to not touch Turing machines again. So the question here is, can you simplify the math part of the proof such that you have a different starting point and then mechanize this? And in particular, Andre Dudenhefner is working on this at the moment. And then work out the foundations. So we all believe that if you write down a decider, this corresponds to a decider on Turing machines. But there is no completely formal proof. There are proofs for parts of this realizability models, for parts of cogs, so with prop, with type hierarchies, with this, with that. We can probably plug them all together. It's possible, or actually I would like to do that, to use metacog to actually verify such a realizability model. Maybe first for parts of cog, then extend to the full cog. And lastly, I've mentioned this, which axioms are compatible. So proof irrelevance should be completely fine. I believe propositional extensionality doesn't actually infer with computation. Functional extensionality should be completely fine. If you're only doing computability theory, it won't work if you're doing complexity theory. More interesting, can you assume classical logic? My current feeling, which has the tendency to change, but is now stable for a while, is that you can assume, for instance, propositional excluded middle, and you will not kill this assumption that definable functions of type nut to nut are computable, but there is no proof of this. All right. So lastly, we're actively looking for more collaborations. This, for instance, make for very nice students projects. So if you want a student to mechanize an interesting proof, undecidability proofs are usually pretty well explained, and there's room for simplification, but you don't need incredible creativity for some of them to do it, so it's very interesting. We have a big graph that you can plug into. All of this is on GitHub. We're very interested to talk to you later in the break, but also, obviously, you can questions now. Thank you.
Okay, first question.
So I have a twofold question. Contrarily to realizability, in dependent type theory, computation and logic are intermingled, right? So how can you trust the fact that by adding some computational power as an assumption, you're not subtly changing the logic and making things provable, whereas they shouldn't have been, or something like that? Like, you're essentially assuming somehow excluded middle by assuming the decidability of a problem, right?
If we're assuming decidability of a problem,
it changes the logic.
It changes the logic, yeah.
So
the library is completely axiom free. The only thing that we have in there are the reductions.
Yeah, right. But that's the whole question. Like how much trust? How would you like the even the model? I think wouldn't be enough to justify that this is legit as a thing. Like depending on your realizability model, it might have like flowing from the meta theory.
So I think what makes it safe is, so we have all these reductions, and you believe the fact that you can extract every coq functions to a computability world. And once you have this, you're done. If you don't
but the function might depend on contrarily to logic, where you stratify saying, here is the undecidable problem. I write a program translation. Now you can actually use the uncomputable power of that thing to create a completely crazy non-uniform machine or something like that.
You don't have any assumptions in there. The functions are functions from base type, which is
right.
numbers to natural numbers.
But they hide. These are coq functions, so they are hiding.
So the proof will not be trivial. I still believe that it works somehow, that you can find a thing. It's also the implicit assumption, essentially every decidability statement in any paper written in coq until now. And it would be really weird if it breaks. I would consider it a bug somehow.
We'll get the paper anyway.
Sure, yeah. So
classically, that's fine. Either way, you're fine.
We'll look into this, and we'll see what you can prove.
And second part of the question is that if you try having like a hyper decidability, Turing jumps and whatnot, what happens?
Interesting. So one thing that might be interesting is to formalize classical computability theory, like all the things you learn in your first course. But then you will have some assumptions. You can, for instance, assume Church thesis, which in type theory means for every function of type nut to nut, there exists a Turing machine which computes it. That's the name of the axiom. Existentially exists a Turing machine, and then it's consistent. Yeah, squashed, exactly. Yeah, propositional existence. Yeah. But also more, you can probably develop stuff like Turing, the hierarchy. You will probably need some assumptions. I would assume you need some axioms that cut down your models to something more computable. But maybe not that many. So that would be interesting. Yeah.
So there's something I don't understand in all this question. That is, there are also undecidability proof in the Isabelle ecosystem.
Are there?
I think I saw one about Turing machines.
So, sure, yeah. So you can also undo undecidability proofs in any proof assistant you want, but then you have to fix your model of computation. And then if you say decidable, you then mean decidable in this model of computation. And then if you say undecidable, you mean not decidable in this model of computation.
So here you just piggyback the model of computation of coq.
Exactly. Yeah.
Okay,
exactly.
That's why the question arises.
Yes, exactly. Oh, good. That's what we mean by the term synthetic. We reuse the notions in coq as the model of computation. Okay, yeah.
And to follow up on that would not work in Isabelle because you can define all kinds of weird functions that you cannot define in coq.
Exactly. So in Isabelle, the situation is a bit more on paper, where nobody writes down a Turing machine. You write down a description of an algorithm and say, by looking at it, obviously it's computable. And that's how you would have to do it in Isabelle. You write it down, and then you require from your reviewers, your users, that they look at it and see it's computable. Or you use an extraction approach again by extracting into some model of computation.
Other questions?
That's a really cool thing about constructive type theory, that you can carry this out, and it doesn't work in any classical logic.
So larger programming projects often have coding and naming conventions. Is it a problem to have similar things for coq developments?
It's a huge problem in this development, and we don't have a convention, and we'd like one. We haven't. I think the thing is we have to pick something. At the moment, we're not. So we have one structure that essentially everybody who wants to contribute a new project that he has done is a new subdirectory in the repository, and then we kind of try to figure it out. I had the pleasure about a year ago to copy together the developments of 7 or 8 papers and make them compile in one repository, and that took a while because you have 7 definitions. I think we have 7 definitions of the post-correspondence problem at the moment, which are somehow equivalent, but also, not trivially so. We have lots of definitions that have the same name, so satisfiability, but there are 7 different logics. So you have to work out namespaces and names. It's doable, it just takes time. I picked a random number, maybe I should say 3.
Okay, one last quick question.
Hey, if I heard you correctly, you mentioned that coq itself is consistent with the axiom that every type is decidable. Is that correct? If you admit this axiom, what are the consequences of that? And does your library still work if you admit that axiom?
So, so first, it's correct because in the set model, it's essentially something like choice. And in the set model, you have choice. Okay. Depending on how you formulate it, I would say it does not. So I would say if the axiom that you write down is propositional, then you might be fine. If you're assuming a real choice function that you have computationally, so something of a function type, and then maybe a proposition saying something, you're definitely not fine.
Okay, let's thank the speaker.